recent years, the phenomenon of dielectrophoresis has been widely implemented in lab-on-chip systems for various measurement and manipulation of microsubstance suspended in the liquid medium. Microsubstance in liquid medium has some important properties needs to be considered. Take polystyrene particle as an example. When it is placed in the solution containing electrolyte such as sodium chloride, the ions will begin to accumulate at the surface of the particle and form a very conductive layer called electrical double layer. The formation of this layer is due to, first, the dissociation of the functional group like sulfate, and second, the ions adsorbed from the solution to the surface of the particle. The ions within this layer are mobile and more concentrated than the surrounding, which makes the particle more conductive than the medium. To perform the effect of dielectrophoresis, AC electric field needs to be applied to the medium, which polarizes the ions inside the electrical double layer, and thus the particle suffers an electromagnetic force. The magnitude and the direction of this force, or so-called the DEP force, varies with the AC frequency. If the particle is driven toward the edge of the electrode, where the strength of the electric field gradient is at maximum, the particle is said to undergo positive DEP. Otherwise, if the particle is driven away from the edge of the electrode, it is said to undergo negative DEP. In general, at low AC frequencies, the particle will be in the positive DEP state. As the frequency rises to a specific value, the transition between positive DEP and negative DEP occurs. This specific frequency is defined as crossover frequency. Since different types of particles correspond to different crossover frequencies, we can design different microelectrostructures to perform manipulation, collection, and separation of various microsubstances. In our lab, we apply the optical tweezer to conduct the experiments. The principle of the optical tweezer is when the laser beam passes through the particle, the momentum of the photon will change and thus exert a radiation pressure on the particle. The resultant force will always drive the particle to the focal point. By this means, the optical tweezer can act like a gripper and a force sensor to trap single particle and measure its crossover frequency at the same time. Besides DEP phenomenon, electrohydrodynamic effects such as electric thermal flow and electroosmosis will also occur. These effects make fluid flow in a certain direction and exert a drag force on the microparticle, which change the resultant force of the particle and increase the difficulty of measuring the DEP phenomenon. Currently, we use the optical tweezer system to obtain the experimental results. Along with the finite element simulation, we are able to quantify the effects of electrohydrodynamic flow and the DEP phenomenon and have a better understanding of them.